In this video, we will explain and demonstrate an EMG circuit. The goal of this circuit is to measure the potential difference across a muscle. We'll use 3 electrodes, one at the top of the muscle, one at the bottom of the muscle, and one on the elbow. The electrode on the elbow will measure the ground, and point A at the top of the bicep will measure voltage with respect to ground, as well as point B at the bottom of the muscle will measure voltage with respect to ground. We want to obtain the voltage difference across the muscle when it contracts. So we will create a difference amplifier that will take the difference between point A and point B. But there are a lot of different signals within the measurement that we're going to be taking. So we'll build a filter in order to filter out only the signals that relate to the muscle contraction. In addition to that, these signals are not very large. They're on the scale of about a millivolt. So we will use 2 amplifiers in order to boost the signal to about a volt. In the end, we will build our circuit, attach the electrodes onto our arm and into the circuit, and use an oscilloscope to see the output measurement of the muscle contracting. So to build the EMG device necessary to take the measurement of the voltage across our muscle, we need to take a measurement at point A and point B. We then use a difference amplifier, which you can see is these 4 resistors, all at about R is 100,000 ohms. So we had R is 100.4K, 99.4K, 100.2K, 101.8K. This device will take the difference between the potential at point A and point B and give us a potential here of VA minus VB. Then the device to the right is a filter. This is a bandpass filter. First it filters for low frequency and then for high frequency. We let R4 be 1.49K, R5 be 181.9K, C1 is 102 nanofarads, C2 is 47 nanofarads. Note that the resistor here is much higher than the resistance here, so we expect most of the current to travel through only the low-pass filter. We have a calculation for F2, the cutoff frequency for the low-pass filter, and it's about 1,000 Hertz, 994.718 Hertz. F1 is the cutoff frequency for this high-pass filter, and that is 19.894 Hertz. This is near the 20 Hertz and the 1,000 Hertz that we need our cutoff frequencies to be at to obtain only the signals that correspond to the contracting muscle. The second part of our circuit is going to take our now filtered VA minus VB potential, and it's going to bring it through 2 amplifiers. You can see the first amplifier here with R6, R7, and R8, and the second amplifier here with R9 and R10. These are non-inverting amplifiers. They have negative feedback, and we know the formula for the gain of a signal that moves through these amplifiers is GV is 1 plus R8 over R7, that is the feedback resistor over the resistor to ground. And for our second amplifier, it's 1 plus R10, again the feedback resistor, over R9, 1 plus R10 over R9. Given the values, R6 is 100.1K, which doesn't matter too much for this calculation. R7 is 1.183K, R8 is 45.97K, R9 is 1.185K, and R10 is 221.74K. we'll get a gain in the first non-inverting amplifier of 39.859, and in the second one, 19.346. These gains are multiplicative, so together that may boost our millivolt signal to about a volt. It would be nice to know the transfer function for our circuit. H of omega is going to be our transfer function, and this is defined as V out over V in. Thankfully, since there are only two parts that are going to add to the transfer function, that is the low-pass filter and the high-pass filter, we can string things along and say that V in, V1, and V1, V out. And what this means is that if we make one measurement along the circuit for the input and after the low-pass filter, and then we do a measurement after the low-pass filter and after at the output voltage, then if we know these, we can create our final transfer function. So since V1 over V in is just the low-pass filter, and V out over V1 is just the high-pass filter, we can say that if we just multiply these two transfer functions together, we get our final transfer function. A note about the amplifiers. The amplifiers produce a gain of about 40 decibels and 20 decibels to our output signal. And so if we like when we write the final gain, we could incorporate those into the log component of our transfer function. But here the transfer function is going to be made up only of the low-pass filter input and the high-pass filter effect. In addition to the transfer function, we're interested in the Bode plots for this circuit. And so the first of these is going to be the gain versus the log of F. And we're going to look at two other Bode plots for two other circuits first. First, if we have a low-pass filter, then our decibel gain versus the log of F in hertz is going to pass the lower frequencies. And as we calculated earlier, for instance for our low-pass filter, this cutoff frequency is our F2. Now, if we look at, oh, and I should note that the signal being passed has 0 decibel gain. Now, if we look at a high-pass filter, and we do that same decibel gain graph versus the log of F in frequency in hertz, here we're going to pass the high frequencies. Again, 0 decibels is the gain for a frequency that passes through. And if we want to know our cutoff frequency, for instance, for our high-pass filter, it's going to be F1, like we calculated earlier. So now we can put these two circuits together, in a sense. We can put these two plots together if we want to know the Bode plot for our circuit. It should resemble something like this, where we have 0 we're basically just adding these two graphs. So where we have 0, we may need to subtract these negative values, or adding the negative values here, and that's how we get our cutoff. And of course this is F1. And this whole axis is log of F in hertz. And then again, where we have 0 here, we have negative values due to our cutoff, and you can see those here with F2. The low pass filter and the high pass filter together are going to add to be a band pass filter, filtering and letting pass through all signals from about 20 hertz to 1000 hertz. In addition to our Bode plot showing gain for only certain frequencies, we have our decibel gain, we have our log of F in hertz, we have F1 and F2 are cutoffs. But here we no longer have 0 as our top point because we have amplifiers. The amplifiers, remember, boosted our voltage by about 40 and about 20. So together that's about 60. So when these multiply together, we get something around 800. For simplicity's sake, take 1,000. If we take the log of 1,000, we get 3. So a log of 1,000 is 3. We know that g of f is 20 log h. And that our 1,000 is going to hang out inside this h. And because it multiplies, we can pull it out. And we get an extra term here, where if we want to say this h is the transfer function I showed previously, we would have an extra term of 20 times 3, adding 60 to every point on this plot. Before our peak was at 0, so now our peak is at 60. This is roughly speaking. In practice, our peak hit something like 55. Again, these are rough numbers for the gain.
This graph is data of gain for specific frequencies that moved through the circuit. You'll notice as the frequencies go below about 20 hertz, or somewhere near 10 to the 1, that there is a positive 20 decibel per decade gain. There's a negative 20 decibel per decade gain where frequencies go about above 1,000 hertz, or about 10 to the 3. In the sweet spot between about 20 and 1,000 hertz, frequency signals experience a gain of about 55 decibels. This is the sweet spot for the signals associated with the muscle activity, which we are interested in measuring and hence have amplified here.
So, alright, I've got the EMG device here all circuited up. If you want to bring the camera in, just like point out some stuff, like the capacitors, you can see as part of the filter, and you can see the op amps here and here to boost the signal, and the difference amplifier here with all these resistors on that amplifier. And so then, so if you want to point it at the, here now, the blue is the output signal, and so when I flex my muscle, we get like a nice 1 volt reading.
That was a huge one, man.
Probably what I'll do is I'll just cut out all this audio and talk over it.
Nice. Huge, man. I got some rippling biceps in there.
All right, I think that's enough.
Do one more, Alex. Give us another like whole series going across this.
Also the back muscle.
Crazy.
heartbeat.
All right, all right.
I don't know. I think that's all I need.
All right. There he is. He's a
That's
smiley, happy
EMG.
camper.
It works.